Okay, in this YouTube, we're going to look at the differentiation of the trig functions. So, for y equals sine x, what's the derivative? So let's have a quick little look at how this plays out. And hopefully we are familiar with the sine curve, like so. And if we wanted to find the derivative of it, as you know, the derivative is simply the gradient of the function. So if this continues on, it goes down here. But we've got, if we're going to graph the derivative, then we would start by finding out where it's equal to 0. So we'd be going through the x-axis at these points because the gradient is equal to 0. Here it's positive, so we'd be coming from a positive point of view. We're coming down, and then it turns negative, and it's negative all the way down here. But there's a point of inflection in here, so the first derivative would equal to 0. So there'll be a little dip in here. So I'm guessing we're going to be doing something like so. And actually, what we find is that here we're going to have another inflection point, and lo and behold, look at the red here is actually, I should have color coded this a little better, because actually what I've got is in green I've got y equals sine x, and in red here I've got y equals cos x. But that is actually the derivative function. I've graphed the derivative of sine x. So what I've discovered here in a matter of 1 minute 44 seconds is that the derivative of the sine function is the cosine function. And that's great. Now if we derived the cosine function here, we had a look at the graph of it. Again, we'd be saying, all right, well, that's now back here, isn't it? Because the derivative here is equal to 0. So it would be back in there. And actually, the derivative is 0 and 0 there and there, because they're turning points for the cos curve. And it starts off negative, so it comes from down here. And actually, sorry, it starts there. It goes negative all the way to there, so it would be negative, and there'd be, there's a little change in inflection. There's a little point of inflection around here. So I'd be doing something along the lines of this, and then I'd be doing the same over this side. And oh my goodness, what have we graphed here? This is sine x. This is sine x flipped in the x-axis, which is y equals minus sine x, and that's the derivative. That's the derivative of cos x. That's the derivative of cos x. So while we're at it down here, the derivative of cos x is equal to minus sine x. All right, that's wonderful. Okay. Now if we can extend this out to the chain rule, so that if we've got y is equal to the sine of a function of x, then we let u equal that function of x, and we say therefore that y is equal to sine u, and we say that therefore y is equal to sine u, so therefore dy dx is equal to, using the chain rule, dy du by du dx, and dy du, right, because y is equal to sine u, is cos u, and du dx is just f dash x, because u is fx. So we get dy dx equal to f dash x cos u, and u is equal to fx, so cos fx. So for a function of x, we will go to deriving that function of x, f dash x, changing the sign to a cos, and the function holds. So for example, the derivative of, should we say, sine 2x will equal 2 for f dash x. Sine goes to cos, and the 2x stays. So that's how it would look. Okay, the other derivative, while we're at it, we need to look at is for tan x, and that is equal to 1 over cos squared x, or sec squared x. And the same chain rule principles will apply to those, obviously. Okay, so they're the derivatives of the trig functions. Excellent. There they are. There. Put a little border around them. Fabulous. Okay, in the next screencast, we'll have a look at the derivatives of the inverse trig functions. But for the time being, we can go with exercise 9b and exercise 9c, starting around about page 440. All right, I'll see you soon.